Okay, hi everyone. It's a pleasure to be here in Krakow and give you this presentation to you. So the work I'm presenting is a joint work with Melinda. She's working at a university spin-off in this project, this Paraphrase project. So we would like to discover divide and conquer algorithms using static analysis. So why do we want to do such ugly things? So what is the reason? Well, of course, because divide and conquer is a standard pattern for concurrence of parallelism. And as you have already heard today, that the next few years we will have megacore computers. This megacore guy gave us very good motivation to have pattern-based programming approach in practice. So we will have to think in parallel when designing applications, and one way to express parallelism at a very high level is using pattern-based approach. So when we use a pattern-based approach, we can rely on an existing library of skeletons, algorithmic skeletons, and if a programmer can use this library, he can express parallelism very easily, and it's more important, he can modify the code or maintain the code more easily if this kind of information is expressed in terms of patterns rather than hard-coded in an application. Furthermore, you can make use of resources much better if you have the possibility to restructure the parallel structure of your application, or you can maybe dynamically modify the parameters to the constructs, the patterns. You have seen this slide already from Kevin. So we are focusing on one particular pattern in this talk. We have tools to discover different sorts of patterns, but in this talk I would like to guide you to divide and conquer, which is actually, if you look more closely, you will realize that it's very similar to the map pattern, because map pattern contains a divide phase and a combine phase, but what's different here is that you do this map pattern recursively. So all this work has been done in Paraphrase project, FP7 project, which aims at facilitating parallel programming, providing methodology and tools to software developers. It fosters the use of high-level patterns. What's very important in the basics of this approach, you have implementation of these patterns which are possible to dynamically remap on the available hardware resources. So it's a really powerful tool in the hand of the programmer. So that's a very simple example of using patterns. This piece of code might reside in an Erlang module that parses other modules. So we read modules, scan them, and parse them in a sequence. We can easily turn this into a more explicit representation of the pattern. So you could say that we have a pipeline made up of 3 activities that are performed in parallel in a pipeline, and you can have multiple instances of this pipeline organized into a task form. The code maybe looks a bit more frightening this way, but it expresses the parallel structure, or one possible parallel structure of the application very explicitly. Let's see another example where we can see how divide and conquer can be put in action. So in this example, you have a radix sort where you sort a list by dividing it into buckets according to some level information. Then you can sort each bucket recursively at the next level, and then you can append all the results together. That's the combine phase, actually. So this is a typical divide and conquer algorithm. How can we express it? Very similar to the previous example. So we could say that a divide and conquer pattern is something that requires a predicate to decide whether we have reached the base case, then a base function that is applied on the base case, and of course the division and the combination. These are again two functions. In a more advanced setting, you could provide some more parameters on the level of parallelism that this construct can provide you. So for instance, you can give an upper bound to the available processes in the construct. Or you can say that after a while of parallel decomposition of the problem, you switch to a sequential decomposition. So very small problems are not solved in parallel, but in sequential. So you can say that the divide and conquer contains a predicate which decides whether it is time to switch to sequential, and then applies a sequential divide and conquer. Of course, you have, again, divide and combine. And in the sequential divide and conquer, of course, you have the same structure we have seen so far. So we have this base function for base predicate, the base fun, divide and combine. So this is how we could formally introduce the structure, the divide and conquer structure in the code. So maybe we could rewrite the previous code into this. So we apply divide and conquer pattern here. So this is, as we have seen, the base predicate. If the list is small enough, then we don't do anything. We just return the list. And the division, the divide function, becomes a bit more complicated in this case. It divides the list into buckets and then attaches this level information to each element in this sequence. The combine function is simply the list's append function. So if we rewrite the previous implementation of radix sort into this one, maybe we can have an implementation of the divide and conquer pattern which is able to dynamically adapt to the available hardware resources or the available number of processors, available energy to the system. Okay, so the paraphrase approach is exactly like that. So we have a system in which we have to identify smaller components that should be somehow organized into a parallel application. We have to understand how these components are related to each other in these in the system, and then we can structure the application into applications of patterns. Of course, during this, we need to restructure the application from time to time. So if we realize that we made a bad decision, maybe another structure would be more appropriate for the given problem or the given resources. We have to restructure the parallelism in the application. And well, this is of course very hard to do with manually. So you should maybe use a software tool to facilitate refactoring. Chris is going to give you a talk later today on how the Paraphrase approach supports this refactoring of patterns. What I would like to emphasize here is that there is a tool called Paraphrase refactoring tool for Erlang, or PARTY for short. This tool is able to locate pattern candidates, for instance, divide and conquer candidate, or map candidate, or task form candidate. But it also allows us to make predictions on the expected parallel speedup offered by the code when the given pattern candidate is turned into a pattern. So what we can do is to prioritize pattern candidates and offer the best possible candidates to the programmer. So that the user of the tool, the programmer, can see a list of possible patterns in his code, and then he can make a decision where to change the structure, where to introduce those patterns explicitly in the code. And since its tool supports the refactoring process, we have the possibility to check whether the functionality has been preserved in the application. So this is one small aspect of this whole approach. We have a pattern candidate browser that allows us to Google the code for patterns. If we go closer to the picture, we can see that, for instance, in a matrix multiplication module, you can see that at this point we could introduce a farm of farms, and that would give us some 6.5 speed up with 12 worker nodes. So the main idea is that we have a framework in which you load the source code into a static analysis tool. It will produce some cost estimates and ranking, and the results, the pattern candidates, are provided to the software developer, who is able to use a refactoring engine to transform the code. But we focus here on the static analysis part in this talk. So pattern candidate discovery is the process to collect syntactic and semantic information, like what is the recursion structure of a given function. And based on these information, it can find pattern candidates like a divide and conquer candidate. Well, this is an example of a divide and conquer algorithm. You can see that the quicksort function calls itself twice. Wow, divide and conquer. Or you can have fast integer multiplication of these strings. Again, the function calls itself 3 times. Or that's a different implementation of the radix sort. Again, you can see that the sort function is defined in a way that it passes itself as an argument to list map, which is responsible to calling it again several times. So that's the basic pattern that we have to observe here, that the function is calling recursively itself many times. Or maybe it's done in a mutual recursive way, like in a min-max implementation, where you have mmmax calling mmmin, and then mmmin calling mmmax recursively. So we are using a system refactoral to apply static analysis on Erlang source code, and then we build data flow graphs and control flow graphs, all these standard things that are defined for many other languages as well. And using these technologies, we can easily derive the rules for identification of pattern candidates, for instance, divide and conquer candidate. Well, the main rule here is that a function has multiple recursive calls to itself. That's what we are trying to find in a code. But this can appear in very different syntactic forms in a source code. So we would like to find all of them. So we would like to describe this problem in terms of data flow graphs and execution paths in the control flow graph and so on, which might be a little costly. For instance, just to decide whether a function is recursive, you have to perform a really sophisticated analysis. There are some ways to optimize things, like some faster rules that can find some of the divide and conquer patterns easier. Like if a function operates in a list, then we can try to find ones that applies itself in the head of a list comprehension, or passes itself to a list map. Or we can try to find something in a function call graph with the function f calling function g, which calls back to f, and function g is recursive. So these are the structures that we are able to discover more easily than the previous very complicated analysis. Okay, so in the future, what we would like to achieve is to not only to find these pattern candidates, but also provide automated refactorings to transform the code from the original implementation to the patterned implementation. This is ongoing work. At the moment, we can't do that. We can do that for other patterns, but not yet for divide and conquer. So once we realize that this kind of definition is really a divide and conquer definition, then the tool would be able to find the necessary smaller transformation sequences to transform this code into this pattern one. Okay, so conclude my talk. I have to stress out that we are interested in pattern-based parallelism, where our work focuses on the discovery of certain patterns in sequential code, and finally in the refactoring of the sequential code into patterns and parallel implementation. And in this talk, I gave you an introduction to how to find divide and conquer patterns, and what the tool can do for us in this respect. And yes, as Kevin said, please look at the project website. You can find many other interesting information on that, not only for Erlang, but also for C++.
Thank you very much. Do we have any questions?
Does your algorithms actually support generation of this parallel code, or just it points to the code that can be written like this?
So you mean that the tool itself is able to transform the code into a new one? We can do that for different sorts of patterns, not yet for divide and conquer, but yeah, if you're interested, I can show you a demo of how to transform code into an application of a task farm, for instance. So there are some simpler patterns that we are able to manually, to automatically refactor. But divide and conquer is more sophisticated because identifying the divide part and the combining part, separating from the rest of the definition, is not very easy. It's possible, it's feasible, we know how to do that, but we haven't implemented it yet.
Okay. No more questions.
Okay.
Okay, so when this is finished, will this become a part of possibly a compiler that will automate?
No. The main idea is not to build it in a compiler, because if you want to be effective, you cannot be precise enough. If you want to be precise enough, you cannot be effective enough. So there is always a trade-off between what the tool is able to do and what is really safe, what kind of transformations are really safe. So if you want to build this into a compiler, you can only do things which are guaranteed to be correct. If you do things interactively using a tool and a programmer working together, you can do much more things. It's much easier to make decisions if you can involve the programmer in the decision phase.
Last question.
So you're saying that you have some estimations of how much performant the code will be. How does it relate to the production code? Do you have any production examples of what the gain was?
I think Chris will give you some examples on real examples. We made some experiments only on toy examples, but the idea is that if you try to do cost estimation, you need, of course, some information on the system on which you will run your application, the final production code, and using that and the cost model, and using some estimations, using some measurements on the sequential execution time, you can make some estimations. But it's always depends on the accuracy of your cost model, how good estimates you have. In practice, it can work properly. So if you have like 3 or 4 pattern candidates which offer you speed up of 10 and other 200 which offer speed up of 3, then of course you will know where to find the possibilities for turning the code into parallel.
Okay, thank you very much. We don't have time for more questions.
Let's have a very short break.